Beep. So let me begin with a word of prayer once I'm going to turn off some of the lights in here so we can see this thing better. Don't go to sleep just yet. I'll pray. Dear Father, we thank you for this day. I thank you for the students. Just ask you bless our work today. Just help us to understand a little bit more about Calculus 3. And I just pray that we would glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So I sent you guys a link to this thing. I think it's pretty handy if you want to visualize certain things. At the moment, I've turned on a vector field. See this M, N, P thing? Like I could put X here, and then it would give me a vector field. This is like plotting the vector field 1, X, 0. And if you wanted to look at less of it, you could, because it lets you maybe just look at it in the z equals. So there's just a plot of the vector field where you're only doing one plot along the z-axis, and then it's doing everything. Anyway, you can mess with the number of vectors plotted, and you can kind of explore what vector fields look like in 3 dimensions if you want. I don't tend to get too much out of those kinds of pictures, but what is handy is what the other thing that's going on here, which is, if I can get rid of this. Beep. This plots here is, and so if you go to the drop-down menu there's different things you can add. So you can graph a surface, you can graph a graph, you can graph a point if you want. You can. So at the moment, I'm looking at a level surface. So the equation that we're plotting is x squared minus y squared minus z squared equals to 2. This is a hyperboloid of 2 sheets. And so you can whee like that if you want, or you can give it a little kick and then it'll keep going if I do it right. There we go. Yay. Exciting, yes. Of course, you could mess with the formula, you could change it to like that. And then you'd have a hyperboloid of 1 sheet, as you can see. Whee. And then you could do weirder stuff, like what happens if you put x squared times y squared and all the same? What does that look like? I have no earth idea, but apparently it looks like this. It's kind of wild. Now, so add to the graph, what if I wanted to put z, I can put z equals to, in this case, g, that's a paraboloid, z equals to x squared plus y squared, see that? There it is. And I could replace it with z equals x plus y. What would z equals x plus y be? That should be a plane, right? And there's the plane. Now we can see it. Now you don't. Now? Not. Anyway, there it is. And you can kind of appreciate the intersection of the plane with that. I don't even know what the name of that thing is, but there it is. And you can also add other things if you're interested, like a space curve. So we'll add that. Why not? So the space curve is it's in there. You see it? Let me I'll turn off the funky one. There we go. So there's a space curve. You can see it's intersecting the plane at different places like so. So you could actually put, one of your specific homework problems, you could easily put the formulas in and look at it if you don't trust your hand to hand, by hand graphing. Let's see here. Like I've told you guys, the twisted cubics, we've done some things with this. Here's what it looks like for reals. So yeah, there it is. It's going out of there pretty fast, right? But there it is. And you could do other things like animate. Anyway, there's tons and tons and tons of features on this website to play with. It's pretty nice. I hope it works on school computers. I have no idea. This is not a Liberty laptop, so it worked. Will it work on a Liberty computer? Your guess is as good as mine. But I have links to other websites, but they've all kind of died because they were all based on Java or no Flash. Some of them are like Flash. Some of them are Java, and just those particular softwares, they age, and then the websites go away. which is sad. But this one lives on at the moment. Now, of course, you could also use Mathematica to do these things, but I don't do that. So if you're interested in how Mathematica does these things, I suggest striking up a conversation with like Dr. Wang. He is the current Mathematica expert here. So anyway, any questions?
We just look up calcplot 3D, should come up, or is it somewhere?
Are you asking me how to find this website?
Yeah.
I made an announcement. There's a link in the announcement.
Oh, okay.
Yeah. Yeah. No, that's okay. It's also like it's also in my website, but let me show you where it is in the website. Like, so here is way down my page, and it's like this one maybe? I don't remember. Maybe it was this one. But like 2 of these don't work anymore. I think the GeoGebra 3D plotter's okay, but it's both better and worse than what we were looking at. So anyway, I really need to kill some of those links. They're dead. But so if you go far enough down, you'll find pictures of my kids eventually. Yeah, they're much bigger now, like much bigger. But anyway, oh, and there's a plot of something. Ooh, yeah. That was using an animation feature. If we look at the multivariate website again, though, just while I've got this out, I wanted to point out to you, I've now covered the mathematics of this. So this is the tangent happens to be red, the normal's green, the binormal's blue in this animation. The little hatchy thing is the osculating plane. The circle is the osculating circle. And truth in advertising here, this curve is obtained by taking a donut and wrapping a curve around a donut. That's how this curve was made. All right. So I actually made the curve by shoving the parameterization of a particular path into the parameterization of a donut. And that gave me a path that wrapped around a donut. That's how I made the equations for it. So this was produced using a software called Maple. Maple's the main competitor to Mathematica. And if I'm going to do something that involves this kind of stuff, I use Maple personally because I have the best tech support for Maple because my brother has been using Maple teaching calculus at Appalachian State for like decades. And he's also kind of like half a computer scientist, so that's handy for me. All right, anyway, any questions? I also have this page down here in terms of visualizations. This is the zoo. And in here, I have some other things I've created with Maple. Like this is an animation of the different surfaces you get from looking at x squared plus y squared minus z squared equals to a constant. When the constant's 0, you get a cone. Otherwise, you either get a hyperboloid of 1 or 2 sheets, depending on the case that you're looking at. So that's kind of neat. An elliptical cone, an elliptical paraboloid, a hyperbolic paraboloid, a hyperboloid of 1 sheet. I just thought it's more cool if they're rotating, so that's why I did this. And, well, this will be relevant later. This illustrates a certain thing that happens with limits, which is kind of nefarious, and another nefarious limit example. Yet another nefarious limit example. That's later. These are tangent vector fields to a surface, but anyway, let me shut up and put this away. Do you guys have any questions? Oh, actually, while I have this out, let's just look at another calculation right quick, and then I'll get back to doing stuff by hand. But just wanted to walk us through a calculation. So here is a path. We could actually plot that using the website I just showed you, right? But you can kind of visualize what this is, though, because it's like the helix we did yesterday, right? It's just we've got e to the t multiplying cosine and sine, and e to the t over here, right? So it's like growing vertically much faster than the helix we looked at yesterday, right? And the radius of the helix, it's not constant anymore, right? It's like growing. So this is what? This is like it's like an exponential spiral, right? Yeah, it's getting bigger and bigger and spiraling up and up, bigger and bigger and bigger.
Like a tornado.
Yeah, like a tornado, exactly. But the calculus here is also more involved because when we differentiate, so first of all, you could just differentiate this without thinking, and that would be foolish because we should try to make use of product rules when we can. And rather than doing product rule 1, 2 times, I can do it just once, at the vector level. See, because I can factor e to the t out and differentiate this, and then I have this plus that, right, by the product rule for vectors times scalar functions. And that gives me this. It's definitely in your interest to factor out e to the t rather than writing it 1, 2, 3, possibly 5 times, possibly 3 times, depending on how you go. Now, this vector, when you look at that squared plus that squared, you get 2. So like this squared plus this squared is 2, so I get 2 plus 1. So the length of this vector without the e to the t is the square root of 3. And then I have e to the t multiplying, so you see the length of the velocity is the square root of 3 times e to the t. You should pay attention to the calculational simplifications I'm making here. Just doing it brute force will make it much, much more difficult, right? So strategic use of some of the hints and tricks I've showed you are very helpful. But anyway, so that's the unit tangent. And if we differentiate, we get dt dt, which is this. Again, I think this is this is a length square root of 2 vector. So this has total length square root of 2 over square root of 3. And so I find that the curvature is 1 over, it's the square root of 2 over the square root of 3. That's the length of ddt, right? But remember, I have to divide by the s dot is another formula. S dot means speed, right? S dot is ds dt, which is the magnitude of the velocity. So s dot it's an old Newtonian notation. Dots are time derivatives, all right? So like s dot is dv dt. And here, the speed is this, right? So this right here is s dot. So that's why I have, hey.
Right there, you have the square root of 2 instead of square root of 2.
I feel like this may be wrong. I think I feel like I should have a 3 there. I feel like this should be a 3 because I should get a square root of 3 from the speed, and I also have a square root of 3 from the magnitude of dt dt. The magnitude of dt dt is definitely square root of 2 over 3, unless I'm miscalculating here. So when I divide by speed, I should have root 3 times root 3. That should be a 3.
Yeah, right over there, you just wrote the square root of 2. That's right.
Oh, this right here? So that's bogus. Because I've neglected, how did this mistake happen?
Forgot the...
Yeah, I neglected the 1 over root 3. So I'm a victim of my simplification. Cautionary tale, yes. All right, so we'll fix that. Anyway, there's the binormal, which we calculate from the cross product. And then, so by the way, let's just appreciate this. What happens as time goes to infinity? The curvature does what? It goes to 0. If you can imagine this curve in your head, it's a tornado, like you said, but it's getting bigger and bigger and bigger. As it stretches out, the curve gets less curved. It gets more and more linear as time goes on. It makes sense that the curvature is going to 0 here, intuitively. Now, the binormal is this monstrosity, and its derivative is that. And if you take the dot product with the normal, that picks off this, apparently. And then I have to do 1 over the speed times this if I haven't made another mistake, hopefully. Now, look at that. There's a 3 here. That's definitely a 3. Anyway, so the torsion is 1 over 3 e to the t. So again, I think it makes sense that the torsion is going to 0 as time goes to infinity because the curve, again, it's getting more and more stretched out, right? It's not, the oscillating plane isn't bending upward as quickly as you get further and further out. Anyway, the double scrolling, it got me. It got me again. This is another thing that I just wanted to look at with you for a second rather than write out. Another interpretation of curvature is it's the infinitesimal rate of change of the angle of inclination with respect to arc length. So if you draw a picture, and my pictures have gotten somewhat, sorry about this. These were better pictures at one point. I don't know how this happened. But if you go along the curve and you go from initial time to time t plus a little bit more, then you can study like how is the angle of that changing. You can study the angle between the initial tangent and the tangent in a little bit more time, right? And we define that angle to be the angle of, let's say, inclination, or phi in this particular context. And I can work out the formula for that in terms of the displacement vector between the tangent vector and its the next tangent vector a little bit of time further. And when I work out this, I end up with twice 1 minus cosine phi. And and so because we're working with infinitesimal time, that means that phi is very small. So I can replace cosine phi with 1 minus 1/2 phi squared to a very good approximation. You might remember that from calculus 2. And then, of course, that just gives me that the magnitude of the change of the tangent vector is simply equal to the magnitude of the angle of inclination. So in other words, that shows you how the tangent's bending through a little time dt. And then if I just do a little chain rule here, I get this formula. Curvature is ds d phi. It measures how quickly the angle of inclination is changing as the arc length. As the arc length increases, well, this is what it does. So like as the angle of, this is kind of backwards from what I want, right? I kind of want to say like d phi ds is 1 over the curvature. That's kind of more what my brain goes towards. Anyway, here's some pictures that sort of exemplify this. Here we have a curvature of 1 over a. And so if we study the circle of radius a equals to 1 versus a equals to 4 for a given arc length, you see what happens. So if I have curvature 1, and if I go over this much length of arc, I'm completely turning the tangent vector around, right? But on the other hand, if I have this much arc and I go over a circle of radius 4, so here the curvature is 1/4, here's the curvature 1. So for a given arc length, the curvature is changing faster. The direction of the tangent vector changes faster, versus down here, the curvature is smaller. The direction of the tangent vector changes less quickly. So that's all I'm trying to say here. It's not much. Anyway, let me put this away and get back to writing. Uh-oh. Hopefully I can find my way back. All right, I'll get it done. Sorry, this part's a little bit complicated. There you go. You good? So last time we worked out something. We worked out that the acceleration, right? It had a tangential piece and it had a normal piece, right? And the tangent and the normal piece, in particular, we had derived that we had like s double dot t plus kappa s dot squared n. All right, so here s is equal to the integral, say from t naught to t, of the magnitude of dr dt, right? I guess I got to use a tau here. I'm feeling guilty about double using the t. So we integrate the speed over time. That gives us the arc length as a function of time, right? So this, of course, also means that ds dt is equal to the magnitude of dr dt, right? Or if you like, it's the magnitude of, in physics speak, the velocity. The speed is the magnitude of the velocity. And just to be clear, we're also using the notation at times s dot. That's Newton's notation. Newton used dots for time derivatives, all right? This notation seems to only live on in physics at this point, but anyway. So of course you might recognize, just standalone formulas here. A sub t is equal to d squared s dt squared, if you like, and a sub n is equal to the curvature, right, times s dot squared, or if you like, it's the curvature times the velocity squared. There's something else to notice here, though. If we have a vector written as a sum of perpendicular pieces, what's the length of the vector? Like, if I was to draw, right, usual example, circular motion, right? So if my acceleration vector looks something like this, right? There's two pieces, right? What are the two pieces? Yeah, you got this piece, which is a sub n, right? Actually, that's not even right. It's because the normal does what? Right. Yeah. So this. My bad. I should write it this way. So I'll make the arrow go the right way. So this is a sub n, because remember the normal points towards the center of the radius of curvature. Yes, sir.
What are the dots above the S?
Time derivative. So like s dot. So s double dot is notation for d squared s dt squared. Yeah. So that's the normal component, but the tangential component, if I had done this right, is this piece, all right? Of course, we don't usually write it that way in physics because we like to write, people tend to write the tangential up here and then normal like that, right? I mean, you might not see this picture in physics, but this is one way we could write the picture. But the larger point here is if I did this correctly, this is a right angle. See, because n dot t is what? Is 0, right? Okay, so what is that? How is the acceleration related then? The magnitude of the acceleration, right, squared, is equal to the tangential component squared plus the normal component squared. This is how perpendicular vectors work, right? The length, it's a right triangle, so the length of the blue and the red squared is equal to the length of the black squared, right? So this is nice. Let me point out to you why. Easy, sort of easy. Royal pain. But we have this relation, so we don't actually have to calculate a sub n directly if we don't want to, you see. Let me give you let's work this out for a specific example. How about the, oh, this thing's pretty horrible. Let's look at the twisted cubic. Right? I want to, so my goal here at the moment, guys, is to calculate, I want to calculate the tangential and the normal components to the acceleration at time t. Oh, thanks. And so let's get to it. And so let's calculate the normal component to the acceleration and the tangential component to the acceleration and speed, right, etc. Let's calculate as much as we can stomach for this thing. All right. So first order of business, the velocity is dr dt, right, which is 1, 2t, 3t squared. So what's that make the speed? The magnitude of that, right, also known as the square root of 1 plus 4t squared plus 9t to the fourth. Well, that's a little bit unpleasant, but there it is. All right. So what's the tangential component to the acceleration? Well, s double dot, right? By the way, this is s dot. So s double dot is 1 over 2 times the square, fine, I'll write it down. It's dv dt, which is explicitly d dt of the square root which is unpleasant, but we can do it, right? So we've got 1 over twice the square root and then we have to multiply upstairs by 8t 36 t cubed, I think. So you could cancel the 2 out and simplify a bit, but I'm just going to leave it, okay? that is the tangential component to the acceleration, right? There you go. That is a sub t right there. Question? No? Okay. How do I find the acceleration? I need the normal. That is
The derivative of
what I want us to get out of our system. Like, the normal is dead to us.
I like the normal.
You like the normal?
Yeah, I like the normal.
Well, you can calculate it. No, it's bad. It's really bad. Maybe it's not too bad for this one, but if I throw an exponential into this, it gets much, much worse. Anyway, okay, so my point is acceleration we can calculate, right? So acceleration, dv dt, is what? 0, 2, and 6t. Okay. So the magnitude of the acceleration is simply the square root of 4 plus 36t squared, right? And, okay, so we know that the normal component to the acceleration is equal to, like, well, you can solve the equation I wrote down over there, right? It's got to be plus or minus the square root of, a squared minus at squared, yeah? So the normal component of the acceleration is plus or minus 4 plus 36t squared minus the tangential component to the acceleration, yowzers. This business, a little bit unpleasant. Starting to think about canceling the 2's. Oh, fine, I'll cancel the 2's. 4t plus 18t cubed over root 1 plus 4t squared plus 9t to the 4th. I got rid of the 2. Got rid of the 2 in the denominator. Since I'm squaring it over here, it's worth my time. So I've got a parentheses 4t plus 18t cubed divided by 1 plus 4t, that was squared. 4t squared plus 9d to the 4th, like so. There you go, that's the normal component. Now, of course, I don't know plus or minus, right? We'd have to do more to sort that out, yeah? That maybe that's the problem. Why this? I was thinking this gives me kind of a circuitous path towards calculating curvature here in a kind of sneaky way. You see? Because the normal component's also equal to what? I mean, we could clean this up a bit, right? This is what, like plus or minus the square root of 4 plus 36t squared times that denominator. I'm not sure what I'm writing is really that helpful in terms of, like, I don't think this is maybe going to give us any kind of really additional insight, but here I made it one fraction. Yay! It's a mess, all right? But the thing is, the normal component to the acceleration is also equal to what? It's also equal to the curvature times the speed squared, right? And that's not that bad. I mean, the speed squared was what? We can see it right from there, right? 1 plus 4t squared plus 9t to the 4th. So if you look at that, I can, up to the sign, I'm not sure about plus or minus, but we can certainly we can find the magnitude of the curvature, right? Wait a minute, how is curvature defined for us? It was the it was, oh. we said curvature was what? It was 1 over the speed times the magnitude of dt dt, right? So, well, I'm not sure. Somehow this plus or minus can't be minus. Yeah, of course. The normal component, you don't have any freedom here, right? Like when we talk about the acceleration vector does not have the option of pointing opposite the normal, center-seeking normal direction. If there is a non-zero normal component, it's center-seeking. It's not possible to have a negative coefficient here. And for that reason, I can drop the minus. So a sub n is greater than or equal to 0 by, a equals to a sub t. Let me go back to the original formula, s double dot, t vector plus kappa v squared n. The thing is, both of the things forming the coefficient of the n, right? These are both non-negative, right? And as such, we can choose the plus here. And as such, this unambiguously, all we have to do is solve that equation for kappa. We've got the curvature of the twisted cubic. This is a much easier way to calculate the curvature of the twisted cubic, I think, as opposed to actually calculating the normal vector and going through all that. Well, maybe, I don't know. I should not get too carried away. Anyway, it's a way of calculating the curvature, which I hadn't showed you yesterday, so there it is. Any questions? So most of you are doing your homework. Most of you are trying the homework. Some of you had like high scores on the homework, but like really low scores on the surprise attack mission. So, I mean, these things happen, but if you're, for best effect, like you must think through the homework, right? Like finding answers will get you points, that's true, but it's better to like reason through the homework as opposed to just collecting answers, right? I mean, points are points, so it's great that you get them, but you really do want to learn from the homework if you can. Let's see here. So I was trying to tell you is we do have time for questions if you have questions, but if there aren't questions, I will say other things. Yeah? So I have more examples in the notes about, physics, but mostly I'm just playing with integration, going between position, velocity, acceleration. Question about parameterization. Go for it.
So, I understand like the concept of setting it, putting in terms of time, but how do you determine how to parameterize different equations? Like the first question, the hyperbola, equation 2, how do we go about figuring out how we're parameterizing?
Well, in Calculus 2, we learned how to parameterize hyperbolas in the plane, right? Stuff like x squared minus 3y squared equals to, say, 1. Like, how would you parameterize that? What I do is I think about what I know about hyperbolic cosh and sinh. I think, oh, well, I know cosh squared minus sinh squared is equal to 1. And once I have this in mind as what I want to happen with my parametric formulas, and so that suggests to me, after a moment's thinking, that I should put x equals to cosh t, and I should put y. Well, I can't put y equal to sinh t because there's a stupid 3 here, but to make the 3 go away, I just take the sinh, and I divide by the natural enemy of 3, which is the square root of 3 when you square it, 1 over the square root of 3. And see, if I make those my formulas, when I plug in, I get this. So I'm working backwards from the algebra I know is how I do it.
Okay. So you just have to remember.
Cos squared minus sin squared is 1, and cosine squared plus sine squared is 1. Yep. Mhm. I mean, there's more, but those are perhaps the most sort of nonlinear ones, I guess, to think of. So, for a surface, if I'm up against something like x squared plus y squared minus z squared equals to 1, I'm trying to parameterize this. First of all, the coordinate stuff I talked to you guys about, right? Like cylindrical, spherical coordinates, not super helpful here, really. I mean, maybe cylindrical is kind of helpful, but what I do here is I see this as, oh, I want this to be my cos squared, basically. And I want this somehow to work out to sinh squared, because then if that's the case, then I got cos squared minus sinh squared is 1, it works, right? So, okay, so evidently I should make z equals to sinh phi here. That'll work nice. But x squared and y squared, well, that requires a little bit more conniving. But what I would suggest then is we would try something like x equals to, say, cosine alpha cos phi, and y is equal to sine alpha cos phi. See, because if I do that, when I square these, what do I get? I get a common cos squared phi, which I'll factor out here, and I get a cosine squared alpha plus a sine squared alpha, you see? And so that's cos squared alpha, which shows you, rather phi, cos squared phi, which shows you if I make those two my formulas for x and y, if I plug them back in, I'll get back to cos squared phi minus sinh squared phi, which I know is 1. So we play these games. And so this suggests to me that the parameterization of this, whatever this thing is, I forget if it's a hyperboloid of, 1 or 2 sheets. It doesn't much matter to me. I can parameterize it by, I think it's 1 sheet actually. Cos alpha, cos phi, sine alpha cos phi, sinh phi. The reason I think that this is a hyperboloid of 1 sheet is I just noticed that my formulas led me to put sinh phi over here, and its phi ranges over all real parameters. That ranges from like minus infinity to infinity, which says to me that this hyperboloid has points in its graph for all possible, you could call phi, well, all possible phi, which gives you all possible z. I think it's a hyperboloid of 1 sheet, actually. So the reason I've added this example to follow up to your question is just like it's the same bucket of tricks, algebra tricks, that leads me to parameterize surfaces as it does to parameterize curves. Now, anyway, the harder problem in the homework is parameterizing that circle on the plane. Do you guys have any ideas about how to do that one? Like there's a problem where you've got a plane, and it's not flat. It's normal vectors like 1, 1, 1 or something, right? This would be wrong. I know. Fine, like this, I guess. 1, 1, 1. All right. That's the normal vector, right? And you're trying to parameterize a circle on that plane. How on earth would you do that? Yeah.
You could choose a perpendicular vector to 1, 1, 1, and then take the cross product of both those vectors.
Oh.
To find.
So you're saying pick a perpendicular vector, let's say u1 like that. I'll make it a unit vector. And you're saying I could take the cross product of this and that and get a second vector, which is.
And then just treat those rather than writing it in component form. You can just write it as like r sine times u1
So you're.
plus r cosine times.
Okay, what's the idea of that solution? What are you doing there? But just to recap, u2 hat you're creating by the cross product of the normal with your u1 hat. Can you guys tell me what should I pick for u1 vector? No. How about, I mean, there's various choices, but you just want a vector perpendicular to 1, 1, 1. How'd you get a vector perpendicular to 1, 1, 1?
Minus 1, 1, 0.
I heard minus 1, 1, 0. I heard you could do 1, 1, 1 minus 1, 0. You could do 1, 0 minus 1. There's many choices, right? Pick something. Whatever you pick, take the cross product of that, it gets you another vector, which is perpendicular to the normal and hence tangent to the plane. Then we just need to think about what we already know. In the plane, in the regular plane, right? You have parameterization like gamma of t is r cosine t, r sine t, right? That parameterizes a circle centered at the origin. If you rewrite this in terms of vectors, this is r cosine t x hat plus r sine t y hat, right? So you take the base point here from the origin as your like starting point, right? And the parameterization looks something like, you know, take your base point, and then you're going to do what? You're going to do like, you know, r cosine t times what? u1 hat's like your x hat. And then r sine t times what? u2 hat. And that's how you could build a parameterization of a circle on the plane. By exploiting the analogy to the regular parameterization of a circle you know in the plane, and just like basically building, what we're doing is we're building like x and y coordinates here using the u1 hat and u2 hat. That's the idea, yeah.
The circle's like really a two-dimensional circle in this because it's on the plane.
The circle is literally a circle. What's complicated, perhaps, is that there's a circle up here. It has radius r. If you were to go down here, it's got an elliptical shadow. There's like an elliptical shadow down here. So I don't know if that helps or not, but like the shadow's elliptical, but the circle is actually, the problem says circle. So if you want to find the equation, you could take the equation of the sphere of radius, whatever the circle was, and intersect that with the plane. You could find Cartesian equations for the circle, but that, and you could use, I mean, anyway, there's other ways of doing it, but I think this is the simplest way. But anyway, have a good weekend, you guys. Please do your homework. Not doing the homework in here is the fastest way to fail this class.